Hello, we're the team composed by Rodolfo Casillas and Rodrigo Valdez. This is for the third partial project, and the problem is let f be the function defined on -4, 2, 3, whose graph, consisting of 3 line segments and a semicircle centered at the origin, is given above. Let g be the function given by g of x equals the integral of 1 to x f of t dt. Now we're going to start with the problem A, which says find the values of g of 2 and g of -2. In order to get these values, we're going to have to integrate using this formula given above. So g of 2 equals 2 and 1, because we are using the x, which is 2, and we are putting the x with 2. Now we know that the integral is getting the area, and we want the area from the point 1 of the x-axis to the point 2. So we need to get the area of this little triangle, and we know that at this point y is 0.5. So we have the height and the length, which is 1. And the formula says that it's the height times the length over 2 for the area of the triangle. And we know that it is negative because it is under the x-axis. So the value is going to be -1 over 4. So we now have the value of g equals 2, which is -1/4. Then we're going to get the 1 of g minus 2, which is 1 over -2, and we know that because this is going from a higher value to a lower value, it is going to be negative, and we can change these two into -2 to 1 of f of t dt, and we now have to get the value from -2 to 1. And for the area of this, we just have to get, which is 1 times 3 over 2. And we have to add the other area of this, which is the radius squared times p over 2, because it is just a semicircle. But because it is under the x-axis, we need to subtract from this area, because this area is over the x-axis, giving us 3 minus p over 2. For each of g derivative of -3 and g double derivative of -3, find the value or state that it doesn't exist. So we have the formula g of x equals the integral of x over 1 f of t dt. When we derivate this g of x, we are left with f of x, because when we derivate, the integral goes away and it's like doing nothing. And now we have just to substitute g of -3 equals f of -3. And on the table, on the graph, we can see that -3 is on y equals 2. So we have the value of g derivative of -3, which is 2. Then for the double derivative, it is going to be -3 equals f derivative of -3. And for this, we just have to get the tangent line, which over here is the point -3, and we can see that the tangent line is just 1. So this is the value of g double derivative of -3.
Point C states, find the x-coordinate of each point of G that has a horizontal tangent line. Since this is the graph of f, we know that G will have a horizontal tangent line every time y equals 0 on f. This means at x equal -1 and x equal 1. x equal -1 and x equal 1. At x equal -1, f goes from positive to negative. This means we have a maximum at x equal 1 and at x equal -1, sorry. And at x equals 1, the graph of f goes from negative to negative. This means g only has an inflection point at that value. It is just an inflection point. It is neither a maximum or a minimum. Point D states that for x between -4 and 3, find all values of x for which the graph of g has points of inflection. This means we need to find points on the graph of f where its concavity changes, or in this case we know that g double derivative of x equal f derivative of x changes sign. So when the slope of the tangent line at any point on f changes, we know it is an inflection point of g. This means we have 3 points at x equal -2, at x equals 0, and at x equal 1. These 3 points satisfy the 2 conditions. The slope of the tangent line of x changes sign at these 3 points, and also its concavity changes. As we can see, at this point they change concavity, at this point they change concavity, and at this point they also change concavity. So we can conclude that G has inflection points at x equal -2, x equal 0, and x equal 1.